Yeah. Welcome to this talk. We're going to be going over group theory, the mathematical foundations of it. A little bit of applied group theory, and then its applications to particle physics. And namely, we'll be going through the rotation groups, and we'll see how this helps us understand things in physics in terms of angular momenta and the CPT theorem, and how they just sort of discovered quarks as well, how that came about as well. All right. Okay. So before I get started, I want to list out the motivation for group theory in physics, and then explore group theory from a purely mathematical standpoint, at least by means of heuristic arguments, because the full mechanism of group theory, we cannot make an exposure of it at this moment. And this lecture is by no means exhaustive of its nature. However, we will approach the key aspects and use them to construct the physics, and how it has helped us also make predictions is what we'll see. So I'll start off with the motivation. So I think before we even talk about groups, I think we should talk about why we even care about transformations. And the reason physicists, quite clearly we care about transformations that change the system but leave the laws invariant. This sort of flows from the second postulate, special relativity. And since Einstein, this has been our major preoccupation. We observe nature, we observe its phenomena, we try to guess its underlying structure as sets. I'm almost tempted to use the word groups of transformations, and how they explain the laws and how they leave them in the same standpoint in different reference frames and different systems, right? So what is a group? We will start with a toy model. Well, this is a triangle, and I've just sort of labeled it 1, 2, 3. And when I say flip about one, so there are obviously two different types of actions I can do. Well, three, but I can either rotate it, and you might also argue that I can rotate it clockwise and anti-clockwise, but you might as well construct this operation from this itself. And the flip about one is nothing to say that if I imagine a line going through one, and if I imagine this to be a mirror, and if I just swap between, so this is all that what I mean by flip about one. Now let's look at a few more transformations, but let's keep this in mind. So if I flip about one, I sort of get this. If I get 1, 3, 2, or 1, 2, 3 arranged this way, I'll get 1, 2. And if I flip about 2, that is to say about this axis, I will get this operation, basically flipping about this way. And if I flip about 3, I will get something like this. Now so these are all our actions or transformations that we're doing to this system that we've set up, this triangle, this label triangle. Now the cool thing is, what happens if we were to combine them? So do one action about after another. So I'm gonna flip about 1, which I get this thing, and I'm going to flip this about 2. Now here's the thing. If I flip this about 2, this is almost the same as this guy right here. Right? I mean, in the sense that what I'm trying to drive at here is all of these actions, combining them ends up to be another element or another action itself. But these actions are not quote unquote commutative. That is to say, if I apply this action A after B, it is not the same as B after A. So AB not equal to BA is the statement we should start with. Okay, so this is just a toy model, but truth be told, group theory is a lot more abstract, and in fact, it's an area of what's called abstract algebra. it's a subfield of abstract algebra, which is an area of math that's been in existence for an order of 400 years. Well, then you may ask, what is a group, abstractly speaking? Abstractly speaking, you sort of go down a hierarchy of definitions. So you say a group is a set of actions. So, our toy model sort of supported this by saying, it's a collection of these actions, and the beautiful thing is if I combine two of them, I get a third one, but they're not necessarily commutative. Or you can say a group is a set with this additional structure of non-commutativity, and this closure, sense of completeness. Or you can say a group is a set which follows an additional rules, a few additional rules, and I mean additional structure, additional rules, nearly the same wording. It's just that instead of saying structure, which is rather a vague term, we're saying it's defined by rules. If you've ever seen Chinmaya's lectures, which we'll link to, is he starts off by explaining a topology as a set with more constraints, and this is something that's pretty common with abstract algebra. So that's essentially what we're doing here. So you have a set, you give it a set of, you put some constraints on how its elements should behave or how some operation should behave. You get an abstract object, and in this case, we want the abstract object to be a group. So we have to set our constraints or rules in such a way. Well, I think this is the right way to approach it. A group is a set and an operation, because I did mention operation because, at the end of the day, combining these is also important rather than just the elements themselves, which follows a few rules. So a group is a set, and an operation which follows a few rules. And so since we've got this in our head, we can quickly jump to the actual abstract definition of a group. A group is basically an algebraic structure. This is a set G, and this is an operation. You can imagine this as a sort of multiplication, but truth be told, it's called a binary operation. So what's a binary operation? It's simply defined as an operation that takes in two elements and it gives out a third one. Okay? That's it. There's nothing more to this. There's nothing more to this whatsoever. It's not, you shouldn't think of this as multiplication, even though it's helpful for us physicists to think of it that way. But it's better to think of it as something that takes two elements and gives a third one. Okay, so closure is the first thing. So you take any two elements of the set G, you combine them, the end result is a part of set G again. And it's also associative. And you have an identity and an inverse. So an identity is basically to say that you combine any element of the set with identity, you get back the same element. Makes no change, and there's always an inverse transformation. You can think of this as multiplying matrices and you ending up with the identity matrix. Okay, and as you can see, commutativity is not mentioned, but I would just make a small note of it here. If your groups are, if this group structure allows elements to be commutative, that is AB equal to BA, it's called an abelian group. But if it's not AB equal to BA, then it's called a non-abelian. All right. And if you've ever read some account of about the Stand model, they would often say that it's a non-abelian gauge theory. Right? We'll slowly approach that in the coming weeks, but the non-abelian part is just this: that the operators or these group elements that are in the group that we are talking about or that we're sort of concerned with, they are mostly non-abelian, that they don't commute. And obviously, for an idea of gauge theory, you can refer to one of the previous talks as to what it is. But in the coming weeks, we'll sort of see the marriage of the two. Right. So let's look at an example of groups, and let's think of rotations. And this is a 2D plane. This is 2D, or to put it in technical terms, R2, just the Euclidean plane. And if we're doing a rotation, this is clockwise rotation. Okay, so let's get to anti-clockwise later, but let's just look at this for a second. And what this means is if I have a vector x vector, and if I want to rotate it by an angle theta, all I need to do is multiply it by r theta, and I will get my rotated vector. And what do I mean by rotation is a good question. Although intuitively we know, rotation is basically, I'm just turning it with respect to this plane, because I'm rotating it with respect to this plane, and I'm rotating it, clockwise. That's it. That's it. But there is a little more structure which I think we should unpack. When I say rotation, the truth is that this is one of the key aspects. My length is unchanged when I rotate. It's a very obvious thing, but I think we should note this down. And this invariance of a rotation is called an isometry, and a transformation that does not change your length is called an isometric. Well. What does it mean then? So if I define x vector to be some ai hat plus bj hat, and my x dash should necessarily be a different point, because obviously in the plane you can see this is a different point from this guy right here. All right, that's the thing. My point has changed, my length doesn't change, and in fact there's a very interesting relationship between them, and that you can derive from the dot product of these two. And whenever I say dot product or inner product, you'll essentially end up with the angles and so on. But this is an interesting thing. So although something as naive as two-dimensional rotation, it should have the structure in it. And we'll examine this matrix first. Okay, and we'll examine whether these rotations form a group. Okay, so let me just write down the matrix. You know what, I'm too lazy. Let's refer to this guy. Okay. So this matrix here, I think the first thing that we should notice about this is we should check at least is it an isometry, or is it to say when I multiply it, does it change anything? So easiest way to check that is by checking the determinant. And why do I need to check the determinant? Is that the determinant essentially when you of a transformation or of a matrix, the determinant, especially of a matrix representing a transformation, essentially tells us what happens to. So if I'm considering a square in like a plane, and my transformation is a skew transformation, which is to say I skew it this way, my determinant will encode by what number of times the n volume is scaled. And if it's in the opposite plane, that's why your determinant has the negative sign. And what do I mean by n volume? I mean, like in the 2D case, it's area, 3D case, it's volume, 1D case, it's just the length of the line. Okay. So necessarily speaking, since we're in a 2D plane, if you want your line to have the same length, your area needs to be constant. This area that is spanned by its components or its length. I was saying, yeah. So it just depends. You want to make sure it's got the n volume to be 1. The reason your n volume should be 1 is because it's an isometry. Your length doesn't change, so you want your determinant to be 1. So is the determinant of r theta really 1? Is the question that we should be asking. And turns out the determinant of r theta, if you can calculate it, it's just multiple of the first leading minus the second leading. The first leading is cos square theta minus of minus sine square theta is cos square theta plus sine square theta, and voila, it's just 1. It's 1. Brilliant. Well, we've got one thing checked out, and it is definitely a rotation. Certainly a rotation. But what we can do right now is we can also think about the transverse of this. Okay, so
An interesting feature is that its transpose is equal to its inverse. And why is this? Because for a 2 by 2 matrix, for a 2 by 2 matrix, if you want to calculate A inverse, it's just basically 1 by determinant of A times the transpose. Right? So, well, here we know the determinant is 1, and obviously, so it's just equal to the transpose. What is the transpose, however? It's a very good question. Transpose is just you swapping the second leading. Swap the second. Okay, and I don't want to do this because I'm kind of lazy with the calculation, but if you did multiply, or if you just square this or multiply this by cos theta, oops, I forgot to switch the signs. Minus sin theta, cos theta, you will again end up with 1. And this is an interesting property for us. This is essentially just this. Actually, it's a little special. It's not just 1. It's the identity matrix. So yes, you have these two properties. Okay, so this property is called orthogonal because, in a sense, when you take the transpose, you are talking about an orthogonal element, and when you multiply the orthogonal elements, you're just ending up with the identity. And determinant of r theta is but 1, and this condition is called being special. And do they form a group? Well, it's pretty obvious that they form a group, and the reason they form a group is because if I multiply r theta by r phi, when you think about this is gonna this action is basically rotating by r theta, this is rotating by r phi, same direction, so it's just adding them. And obviously this is yet another rotation. Obviously it is going to follow these properties, so it does indeed form a group because you have the identity, you have an inverse, you have this closure property satisfied as well. So these elements, these rotation matrices, they are called SO groups or special orthogonal groups. And this group that we just considered is called SO2 because you have ideally 2 degrees. I'm sorry, what was that? So that I'm muting you because there's some noise from your end. So essentially it's just as I was saying, it's 2-dimensional, 2 degrees of freedom, so you call it SO2. 1 second please. One sec guys, sorry, having some trouble at home. On these days. So yes, just to carry on with what I was saying, essentially this is a group and this group is called the SO2. Well, you might wonder, is this the only group that does rotations for us in 2 dimensions? Well, the answer is no. You've got a more interesting group, and I can sort of prove to you that you will indeed get back this matrix from that group. So it's just a short proof. The group is nothing but the U1 group, and the elements of U1 are basically this e power I theta. We kind of, if you've watched any 3 blue 1 problem video, e power I theta is essentially anti-clockwise rotation. It rotates this way. So theta being the parameter of the rotation. Right? And e power I theta can be written as cos theta plus I sin theta. Now, here's the thing. I can sort of rewrite this as I cos theta plus small I sin theta. I'll get to what these mean. So I is essentially just the 2 by 2 rotation, identity matrix, so it's just 1, 0, 0, 1 cos theta. Okay? Sin theta on the other hand, it's a little more special. So I'm going to define I to be this matrix. Okay, might look familiar. The property of this is if I get I squared, which is 0 minus 1 0, I will actually just end up with minus 1, which is minus I. And this is essentially the property of I, because in normal cases we define I to be the square root of minus 1, and it's defined as I squared being minus 1. So I've just defined it in a matrix sort of form, and if I just substitute this here, 0 minus 1, 0 sin theta, it's quite easy to see that I'm just going to bring these days here, that cos theta plus, cos theta 0 0 cos theta plus 0 minus sin theta 0 is essentially just the same matrix. I've just got from a matrix avatar of this matrix avatar of e power I theta to the rotation matrices we were just looking at. So they are in fact, in a sense, very equivalent, and they obviously do represent the same rotations. And the reason this is called U1 is because if I take an element U of U1, U belonging to U1, the thing about U is that U dagger U, which is to say U the whole, U conjugate, complex conjugate transpose times U is just that, or 1, or it's basically the identity element of the group. We'll see how this is true, because if I take U to be I theta, U dagger is nothing but minus I theta, and this is obviously just 1. So this is called and this condition is called unitarity, and we will sort of visit this in quantum when we're discussing about quantum mechanics. But essentially, this group is the unitary group of rotations in dimension 1, right? So we've sort of shown that there is a correspondence between U1 and SO2. Now here's the thing, here's a problem. Okay, we've always talked about things that were continuous, which is theta lies between minus 2 pi and 2 pi for our considerations most of the time. Well, the thing is, you can have this parameter can be very arbitrarily small because we're only considering real numbers, and I can have an infinite number of numbers between these two regions. I'm sorry. So yeah, these are quote unquote continuous parameters, and thus these groups have infinite number of elements, and that is problematic. So sometimes it's easier. Okay, so it's easier to deal with a different type or a different way of interpreting the group versus just the group itself, and that is what we will do in Lie theory. So Lie theory is primarily just Lie groups, which are infinite groups, just as we saw, plus something that's called Lie algebra, which we will discover as to what it is. So first we'll consider a situation. So if I have a rotation, and if I consider my rotation to be very small, very, very small, if this is my axis, I'm just going to be considering to be a very, very small angle, okay, very tiny angle. And so that would mean it's a small displacement from the identity transformation. It's a small change from doing absolutely nothing. So this is how I would write it naturally. And this is a small number. It's very, very smaller than 1. Another way to write this in terms of the parameter theta is to say, well, obviously you can ask me, first question is, why do I care about this? Because I can sort of consider this to be a very small building block, and if I want to build up transformations that are finite from this very infinitesimal transformation, I can repeat these infinitesimal transformations n number of times to get something that's actually finite. Okay, so that's pretty obvious. So if I have a very small, so if I'm counting 10 centimeters, I can just count 1 centimeter 10 times and I'll end up with the same thing. And I can incorporate this by saying this finite angle theta is split into n, which is where n is a very large number. So this fraction ends up being very small as a whole. This condition is thus satisfied. So if I want something finite, then I will have to do something multiple times, and doing it multiple times is just multiplying the same thing over and over again. So I will get something like this. Just multiplied it n number of times. Here's the beauty though. If I really want to see what happens in a limiting case, all I have to do is shove a limit, n goes to infinity, okay, where I'm just trying to get this to the most infinitesimal thing. This is going to be the smallest transformation ever, and that's what I'm trying to analyze here by shoving this limit. So I'm just going to try to understand what the hell this building block is, and essentially this is, if you look closely, just the exponential, or alternatively it's written as theta g. Okay, just to I heard some noise, please mute yourselves. Thank you. So essentially this g is what you call a generator. And why is it called a generator? Because I can break this transformation up into identity plus a very small coefficient and this generator matrix. And essentially any transformation can be broken up as e power theta, where theta is the input parameter and g being my generator. And obviously the first question you should be asking me is, how the hell can I think of e to the power theta g? Kinda crazy. But don't think too much. Don't think of trying to raise the matrix to the power of e. Instead, think of e as just the Taylor expansion. Okay? And just the thing, although we can describe things this way, it's physics tendency to add an I before this. The reason we add an I before this is to maintain this condition that's called hermicity. Why do we need hermicity, something you may ask? Because quantum mechanics, this is something that comes from quantum mechanics. Quantum mechanically speaking, hermicity is nothing but just this, where all the operators are just self-adjoint operators. Basically, they are equivalent to their own daggers. And the reason we do this is twofold, because once, as we'll see in the quantum mechanics section later on, all of these eigenvalues are real. I'll explain this in a moment. And this eigenvectors, they form an orthonormal basis. We'll get to this. Don't worry about this. But essentially, you should know that we add an I here usually just for the sake of this physical condition. Okay, and essentially, if you want to talk about how we expand this out, it's just this guy. So you Taylor expand. I can't seem to remember the actual form, but you would get something like g squared by 2 factorial minus I g cubed by 3 factorial and so on. It's just the Taylor expansion, nothing too freaky. Right? So this is the first step towards getting towards Lie algebra. What do I mean by Lie algebra? So as I was saying, the question that we're trying to tackle here is what can I do instead of dealing with these infinite elements, infinite number of elements. Essentially, we can talk about the generators that generate these transformations, because instead of talking about just these things. So well, it turns out for each type of transformation, which is to say, if I have in 2 dimensions, you have 2 different types. You have the clockwise and you have the anti-clockwise in a plane. You can talk about 2 different kinds of generators, 2Gs. And these 2Gs are they are most fundamental ones, in the sense that you can take up other generators. So I can call them Gi and Gj. So I have 2 generators, and using these 2 generators, I can basically create a I can do where alpha and beta are just some random. By means of the linear combination of these, I can generate other generators. I can create other generators that can therefore kind of just map out the entire set. Okay? So these 2 can be considered as a basis in a very loose sense. Okay? So the reason this is so helpful is because there are always a finite number of generators, whereas there are infinite number of group elements, and these generators usually form what is called a generator algebra or a Lie algebra. So usually this is something that you would see in the groups that we're dealing with. Usually some Fij, where Gk is just another generator, and I can basically talk about the relationship between them and between the bases, and I can also talk about the relationship with other generators by creating linear combinations of these 3, where Fij is just some number that's called a structure constant. So where have we come? So instead of talking about all of this mess, we can just neatly talk about this basis and this relationship. And all of these elements can be built from just these 2 things. Just these 2 sets. This set, and this is called an algebra because this is, in a sense, you can think of this as the commutator. And I'll explain why. Because usually you define a Lie algebra, axiomatically speaking, as a vector space over some field with this operation, and this operation is nothing but the commutator for us, because we are always talking about matrix. So we call this the Lie bracket, but it's essentially just the commutator, and it follows these rules. And uniquely enough, it's a vector space, and if you want to get even more technical, it's actually a differential manifold. So essentially, a differential manifold is a geometric object. So instead of talking about an algebraic object, which is the group, we can talk about the geometry of the vector space that this Lie algebra creates, and this is something that we can be a little more comfortable with for the reasons I stated before. Alright? And just one more thing that should have rung a bell early on is, whenever we're talking about e power I theta, if I am multiplying with some e power I phi, I usually can just do this. Can I do this? Is a good question. You can do this in this case, but if I'm going to consider some 2 random parameters, e power I theta g, this is a generator, this is a different thing, and this is a different algebra. Is this equal to the question mark? I'll put a question mark here. Sorry, theta. Is this true? Well, turns out this is true provided we have this condition, where if you take the commutator of them, fg minus gf, it should be 0. Otherwise, you have a more crazier formula to work with. E power I, for this same guy, just put an equal to. This is called the BCH formula. We won't need the proof, but we just need to know of its existence. According to the BCH formula, you would have a really weird way to write this, which is let me just try to recall that. It's too complicated. You would have e power I theta times just the first transformation plus just the first transformation plus the commutator of the two divided by 2 plus and so on and so forth. This doesn't really matter like the whole formula for our present case at least, but you should know that if you want to combine these two elements, because technically speaking it is a vector space, so vector space is closed, you have the same axioms, you can't get away with such a simple thing. It's a little bit more complicated. It's called the Baker-Campbell-Hausdorff formula, BCH. Maybe we can discuss this in after the lecture, but this is basically all the elements of E theory and group theory that we will require. And there is something called representation theory, wherein we talked about 2 by 2 matrices as being elements of SO2, but the case is that I can also have 3 by 3 matrices being elements of SO2 or 4 by 4. It just needs to be a square matrix for some neat set of properties. But you can represent these elements with 4 by 4 matrices. But the truth is that this is, for our purposes, the most fundamental representation of the thing. Okay, nothing else matters. So, in a very technical sense, since we've already talked about the vector space, a representation is nothing but if I'm going to represent SO2, the representation of the identity element must be the identity element. If I take the identity element here, and if I want to talk about the 3 by 3 matrix of that, it must be the 3 by 3 matrix of just ones and zeros. And if I take the inverse of an element, it should be the inverse in terms of this representation. And if I combine two representations using the same binary operator, I should get the representation, of this guy. So these are the three rules if you want to follow, if you want to build up some larger representation or a different representation, right? And in fact, what happens if we consider the vector spaces, we have something called an invariant subspace. So what happens is, if I act on if I consider that a subspace is basically just a part of the larger vector space. It's a smaller vector space. In a sense, it's a part of a larger one, and it also obeys the axioms, and obviously it has the same axioms as the algebra that we're considering. But the beautiful thing about this invariant subspace is that if I act on this with either any of the arbitrary representations or any arbitrary group element, its elements don't change, its algebra doesn't change. And why is this important? Why do we care? Because you can use any of these representations to describe nature, but there's just one particular thing that we care about, and the things that we care about are basically the representations that leave the space, this invariant subspace, that just leave a particular subspace invariant, and this particular subspace that we consider is not a just the smaller one, but we care about the trivial one being just the identity element and the entire space itself. I know it's kind of stupid to talk about, the entire space as being subspace of itself, but it's a larger requirement. So the representations that do this are called irreps or irreducible representations, and you will see later on that every single particle in nature is described by these irreducible representations, and we have something that's called a Casimir when we're talking about quantum numbers. So we'll get to that. So I think we'll do a little bit of quantum mechanics before we head ahead. So in quantum mechanics, everything is about this object that's called the state vector, and essentially it's got all the information that we care about in the system, and if I apply the Hamiltonian operator to the state vector, I will find out how it evolves in time. Okay, so this is the first thing that you need to know about quantum mechanics. The second thing is, if you want to find out the property, let's say momentum or position or something, you want to talk about the operator corresponding to the property that's being measured. So this is the property. And when you act on the state vector with this thing, then you will discover what that property is held by the system. So state vector describes system, but if you want to describe a particular aspect of the system, you have to act on it within matrix O, and we call these matrices the observables, since they correspond to things that we can actually see or measure. But the beautiful thing is, when you act on it, you usually end up with something like this, where this is called an eigenvalue, and this is essentially just a real number. And it is a real number mostly because of the fact that, not mostly, entirely because of the fact that this is a self-adjoint matrix, as we saw earlier. This is the adjoint operation, and it is its own adjoint, so it's called a self-adjoint. And these, I can put a lambda I here as well. The thing is, these guys, if you take the inner product, these guys, it is defined like this, in a sense that they are perpendicular. That is to say, if I take lambda I, lambda j, and this is a very, very loose notation, not to be written this way, but just to give you guys an idea, we say cos theta. This essentially just changes to lambda ij, because if they are perpendicular, this will go to 0, but if they are not perpendicular, this will just become 1, because we're just at the end of the day just multiplying their own magnitudes. And what else should we talk about? Quantum mechanics. Just as a side note, in the position representation of things, the operator that corresponds position is just x, and momentum it is just psi h bar. Obviously, not going to include the time component because we're dealing with things non-relativistically here, but this essentially is just the gradient. Okay, just 3 gradient, not the 4 one. And a very interesting thing in quantum mechanics is things are probabilistic, and this lambda I absolute squared can tell us the probability of us observing lambda, and this is called Bond's rule or Bond's postulate. And due to this, we want all our lambda squared sums to be equal to 1, or and sometimes we have and this is called normalization, or this is said to be normalized if it all adds up to 1, because when we're speaking about probabilities, we definitely want things to add up to 1, otherwise it makes no sense. Alright, so this is just a very quick run through of the quantum mechanics that we would sort of require. Okay, and if you have any questions, you can sort of pop in when we're talking about things in quantum mechanics, or lead theory and stuff later on. Now, I want to talk a bit about spin. It's weird, man. It's just weird. The simplest thing about spin you can say is that orbital momentum is a number described by L, and usually it's it's the set of values. It can range from go from minus L to plus L, and it goes in integral values, which is to say it goes from minus L plus 1 minus L plus 2 to 0 plus 1 2 3 and then L or whatever. Okay, but then spin, however, is a set of Corner numbers that range from, it can go from minus S to S by 2 minus S by 2 or so on and so forth. It can be half integral is the thing. But what on earth are these things? It's so bizarre that we're randomly just talking about these things. So let me just consider an atom, a very simple one, a hydrogen atom. Okay, this is obviously electron, this is a proton. One moment please, let me just get some water. Essentially, your electron is gonna have some angular momentum because it is spinning around. Okay, so it's gonna have some orbital angular momentum, whose operators are given by L hat. Okay, so when I apply L hat on some side, I will essentially just end up with there is a h bar factor here, but I'm not going to talk about it. I'm just going to set h bar to 1 for the sake of natural units. Okay. And what's up with spin then? Well, spin is pretty similar case only. What happens when you apply it on, sorry, you get S plus 1. But as we've seen, S can go from 1 to 2. And what is this S? Physically speaking, what does it mean? The thing is, when we're talking about, let's say, a cube, okay, a cube that is non-deformable, that to say I can't crush this cube, what are the degrees of freedom it has? I can rotate it this way and this way about the 3 axes, and the other way around. I don't know how that works, can't really visualize it, but essentially you've got 3 degrees of freedom, or 6, sorry, because you have 6 degrees, and you can rotate about that clockwise or anti-clockwise, so 6 times as well. Spin is essentially just the degree of freedom that is intrinsic to the particle. What do I mean by that actually? And what do I mean by saying spin is a form of angular momentum? So there's this one interesting experiment that's called the Stern-Gerlach experiment. So what they did was, this is a very peculiar type of magnet. Well, what happens is, if your if I chuck a magnet here and if it's oriented upwards, it will, and this is a north pole and this is south pole. If it's oriented upwards, which means this is the north pole and this is the south pole, it will flip it and it will send it out. Okay, and I can sort of make observations here. But what happened was, when they sent in silver atoms which had no angular momentum, just plain electrons, they still observed the fact that they were being split up, 50-50. Half of them spin up, not spin up, like half of them were other polarized state upwards, other polarized state downwards. That's gotta mean there's some intrinsic magnetic property. So essentially what they posited early on is that there's these things are spinning about their own axes, but then for this to make sense physically and for this effect to be so, because it just splits up immediately, there's no time delay, there's no effect of thinking of this as a very small point particle as it should be. Instead, it's treated almost like if it's some mass, it's a big thing. So technically speaking, if you have this spinning picture in your head, that would mean your electron would have to be very giant and it would be a massive particle, which makes no sense. Absolutely nonsensical. So the picture you should take is that when you're thinking of this, you should think of spin as an internal degree of freedom that is a form of angular momentum. And in fact, when you, the angular momentum is, as we've seen in the previous lectures, the angular momentum is it corresponds to uh, rotations, and I call it the generator of rotations. Let me explain the statement. From Noether's theorem, there's always, if for every conserved quantity, there is a symmetry. So if there is rotational symmetry, the quantity that is conserved is the total angular momentum. But here's the thing, when scientists observed, it's not the orbital angular momentum that was being conserved. It was never conserved. So the only thing that's always conserved in the case of rotational symmetry is L hat plus S hat, which is the sum of the orbital momentum and this weird term that is intrinsic to every particle. Okay, so this is also how you would sort of classify things into fermions and bosons, because fermions have half integral spin, as in they would, the spin of a fermion would always be 1 by 2, 3 by 2, and so on, 5 by 2, and so on, whereas bosons go from 0, 1, 2, 3, and etc. Alright? So, with this we can actually sort of think of, okay, yeah, before we go there, very interesting tidbit, not really very important for our discussion, but we just discussed rotations, spin, of angular momentum, and quantum mechanics, and there's this normalization condition. But have you ever thought what happens if we were to add angular momentum? I mean, if they are in the same, if I'm adding something like Jx, which is to say I'm measuring the angular momentum about the x-axis, and if this was also Jx but of a different direction, it's pretty straightforward. You just gotta add them. But then another thing comes in where, I want all of their coefficients in front of them, all of these eigenvalues, these guys, when I'm adding them, they should be normalized. They should add up to 1, all of them. So what we do is, we have, this is a case for, if I'm adding a spin 2 particle with a spin half particle, depending on the orientation, you would rather just refer to this table. And these are called Klepsch, I'm spelling it right, Gordon. Coefficients, just a fun thing that sort of connects these two ideas that we just discussed about. There is obviously a way of calculating this. I don't want to go into it, but essentially when you're thinking of this, you should also think about the normalization, which you will infer from this table or by doing some very weird complex calculations, or you could, if it's, and you should also think about the alignment of the two operators as well. Yeah. So there's a very intimate connection between SU2, the group, and spin, and we will review that here. Okay. So what is SU2? SU2 is essentially special unitary matrices of 2 dimensions. And who are the elements of SU2? The elements of SU2 are essentially the Pauli matrices, because again, you can create a group out of these guys, because if again, I need to consider the identity matrix and the other Pauli matrices, and we just to give you guys an intro as to what a Pauli matrix is. A Pauli matrix sigma I, when acted upon this guy, will just essentially give me the spin along that direction. And in fact, the S hat that we were discussing here, the S hat is defined as S hat high, which is Sx or Sy or Sz along the direction, is just sigma I by 2. So these guys do form a group, and if you just look at the matrices, it's pretty obvious that they are unitary in the sense that U dagger is 1, and they are special in the sense that well, they are not well, yeah, okay, let's just say that for a second. Let's just keep that. Let's not go into too much detail yet. The thing that we about is I'm just bringing this here to note something that's called a I'm sorry, wait, I'm just looking through my slides for a second. Okay, cool. This is the direction we're heading in. Okay, I won't need the next slide. Just gonna keep it very short and brief. This SU2 gives us everything that we need to talk about internal degrees of freedom. That is the internal degree of freedom here in case in point is spin, and it gives us all the symmetries that we need for it. And the cool thing about this is the SU2 is the SU2 and just the group that forms 3D rotations. SO3 has a link, and the link is, you cannot see it from the group elements, but I'll just write down their algebra. So the algebra for this the SU2 group is, if I have a Pauli matrix, this, the third Pauli matrix. It's just this guy. This is the algebra. This is the Lie algebra behind this group. Whereas if I look at the SO3 and if I look at just the angular momentum as the generators, I would get something like this. Very similar algebras, except for a factor of 2. And that's what that I don't want to go into too much detail because that would end up us going to topology. But to put it in very naive terms, it's a 2-to-1 map, or it's called a homomorphism. It's basically a map that has no inverse but preserves the structure of the group. Basically, we are talking about rotations in both of these cases, but the weird thing is, you need, if you want to go from this group to this group, you need 2 elements that would sort of correspond to the guy here, and that's kind of obvious by means of the algebra where there's a 2, there's a factor of 2 that's involved here. And in fact, this is just us talking about spin half, because they are just the Pauli matrices, and the Pauli matrices essentially just tell us about spin half particles. But the SU2, from a representation theory point of view, as a one-dimensional representation corresponds to spin 0. A 2-dimensional representation corresponds to spin half. Oops. 3 dimensions corresponds to spin 1. And why do I care about this? Because in spin 0, there's only just 1 degree of freedom. It's always 0. The spin is always 0. Spin half, I'll show you guys why it's called spin half now as well. But in spin half, essentially there are 2 degrees of freedom. Your spin can be -1 or +1, and it's pretty obvious when you see that you can be this side of the axis. But in spin 1, you have 3 states you can be in: +1, -1. But why is this called spin half? Apart from this factor, essentially, when you want to talk about matrix, the exponential map that represents this algebra, well, I would describe it as m theta, and you just raise it as, this is, we're going to do this operation, and the parameter is theta, and the operation is, for example, we'll do sigma 3, and the sigma 3 matrix is nothing but 1 minus 1, the rest is zeros. Okay, and we're adding the I here because for homicity's sake. There's a small theorem in math wherein if you have a diagonal matrix like this, and you want to exponentiate it, you can just exponentiate each term. I think this also works with upper triangular matrices, not too sure. But essentially you just need to take e power I theta of of each term here. So e power I theta of each term here would just lead us to this matrix. And there's a factor of 2 here which I forgot conveniently, haha. That comes from the algebra. And the reason we have this 2, you might think it's kind of weird, but if I just have the I, if I have the sigma I, sigma j, the thing is you get a factor of multiplying by 2 here, and we really just don't want that, because it's sort of scaling it in a very weird sense, and we want to talk about relations, and we want to talk about the length being preserved, not being scaled. And that's kind of it's kind of a weird wonky relationship. There's no simple correspondence, but here if we do this by 2 we get that. That's why we have a by 2 here. But then the consequence of this by 2 is this 1 by 2 is very interesting. So let me just exponentiate this. So I do e power I theta by 2, then e power minus I theta by 2. You can see why. Now if I put an argument 2 pi here, and if I have an argument 4 pi here, there's a distinction. If I put 2 pi here, I'll only get e power I pi here, and I'll get a minus. I'll end up taking a minus outside. So essentially I'll get minus I back. Whereas if I put 4 pi, I'll get I back again. So this is kind of counterintuitive to us thinking about, if I have a circle, and if I go through it by 2 pi degrees, I'll end up back to the starting point. Wrong. With the spinner, I'm sorry, with this this representation of this group, you need to go by 4 pi, and this representation is called spinner. We will deal with this a little bit more in the next lecture when we're talking about the Dirac equation, where we'll have to talk about spinners and gamma matrices and so on. But for now, you just need to know the spinner is a very interesting representation of the SU2 for spin half particles, and the reason you call them spin half is because the spinner in this case, spinner is a little bit more smarter than a vector, because it can tell whether if your argument is 2 pi or 4 pi. One way to visualize this is to say that if I have 2 objects connected by a small thread, if I rotate this by 2 pi degrees, I'll have twisted this, and I will not have come back to the same point. I'll need to twist back again by another 2 pi, ending up for total magnitude of rotation ending up to 4 pi. But again, this is just a very good analogy. So in summary, a spin L object rotates with a 2L plus 1 dimensional representation of the SU2, and L is essentially just 0, 3 by 2, so on. So yeah, this is essentially what it is, and we will be coming back to this spin group a lot, since it really just describes the nature itself, and the symmetry is very readily embodied, and we've seen how the representations can play out. Okay. Before we head ahead, I just want to talk about a concept that I mentioned earlier. I did promise you guys that I will explain quantum numbers to you, and they are the most basic idea is in QFT is you want everything to be Lorentz invariant. So if I apply my 4 momentum operator on some site, I get an eigenvalue, this is not Lorentz invariant. No. This is definitely not Lorentz invariant, because the only quantities that are Lorentz invariant are, as we've seen earlier, this is Lorentz invariant, this is Lorentz invariant, and so on. Okay? So this is exactly what we're going to do. Now, if I want to construct something Lorentz invariant from an operator, I will just apply it twice, and this will result in something like this. And if your particle is at rest, we know that p mu, the first component of p mu is T, and the rest would just be zeros, and this would just correspond to the energy of the particle. Interestingly enough, if I square my spin operator, okay, where my spin operator was defined as SI was defined as sigma I by 2, if I square it and sum it over all the i's, this is something I do, and I define this as squared, it's just sigma 1 squared by 4 plus sigma 2 squared by 4 plus sigma 3 squared, sigma 3 squared by 4. It's just, and weird thing about the sigmas or the polymatrices is if I square them, I'll get the identity back. That's called involution, I think. But essentially, this is just the same as saying I by 4 plus I by 4 plus I by 4 times. This is just I go for 3 times, and I'm just going to get 3 by 4 I back. The weird thing, the really weird thing is this 3 by 4 might seem arbitrary, but once you consider the fact that our spin is given by the eigenvalue in this structure, it becomes obvious that this is actually corresponding to a spin half, because you have 1 by 2, you get 3 by 2 here, multiplied by half again, you get 3 by 4 back again. So essentially, when you square the operators this way, the sum of squares of operators are called the Casimirs, and each eigenvalue of a Casimir, like Rishi will show you later on, the Casimir for charge conjugation is the most easiest to sort of express. If I take the charge, if I operate the Casimir of the charge, this is the charge operator, that's it, okay, and it's a Casimir. Now if I put it here, my eigenvalue is nothing but minus e, and this corresponds exactly to one of the quantum numbers of an electron. Okay, and in fact, this is how we created quantum numbers. So this classification of Casimirs, which is basically the sum of squares of operators, and their eigenvalues as representations of physically observable things. Again, I can measure minus e, I can measure my spin, I can measure my energy. These are all things that are very much present in nature. And another interesting thing about any Casimir C, not just a charge guy, is if I take an element of the group G, the commutator will be 0, because, for example, this, and if I'm considering all the group form from all the momentum operators, this is obviously going to be 0, because obviously they commute, right? This is a scalar at the end of the day, just for an example. Okay, so this classification is called Wigner's classification, and each Casimir corresponds to a physically observable value or a quantum number. Isn't that beautiful? It is. And with this apparatus, Heisenberg actually suggested something. So he actually saw that the mass of a proton and neutron was very close, and they had the same spin, but they had a different charge. So he suggested that there must be a form of an SU2 symmetry present between a proton and a neutron, and he called it he first started by constructing what's called a nucleon state, and then he called this symmetry isospin because this is the spin group, and he said that they must have some spin kind of a symmetry. Excuse me. So what he did was, first he constructed what's called a nucleon state, and the nucleon state is given by something like this. So you get NP, or actually this is called PP, proton proton. So we're considering two particles here. So proton proton plus neutron proton. Plus you know. So, but very naively for a single particle, for a single thing, you can just say that okay, it's in superposition of being either a proton or a neutron. But even more widely so, you can construct something that's even weirder for a larger configuration of things. Now obviously the interesting condition is just the normalization condition pops in automatically, and what he proceeded to do is he sort of constructed this operator U. It's essentially what's called a projection operator. What is a projection operator? It's basically just projecting so when this, for example, acts on this, the way you should think of it is it's inner product of P with P, which will just end up being alpha, and scaling the P itself. So if you're talking about a space where P is a basis and N is a basis, this guy is just projecting some vector onto this axis, and the number it's multiplied by is scaling it. So that's a projection operator. So he did some constructions, and what he saw, I don't want to go through all the details, was what he saw was there is an SU2 symmetry. There is an SU2 symmetry in between neutrons and protons, where there is no electromagnetism. There should be no electromagnetism. There is an approximate SU2 symmetry. What Heisenberg suggested, based on the group theory picture of neutrons and protons, and from what we've just discussed. Because it's quite natural to wonder that, okay, my eigenvalues are oddly so close, so they must have the same Casimir. That's thinking that went in Heisenberg's head. But you can get even more complicated based on just this projection operator and constructing all of this, and that's exactly what Gell-Mann, what he did was he essentially sort of, whoops, this is the wrong diagram, but essentially he deconstructed things into what's called a singlet and a doublet state. Which I can show you guys. But in a singlet state, he saw that if you consider systems of two particles, and when you act on it with this particular operator, you would either get a singlet state or a triplet. Sorry, not a doublet, a triplet, which would be three different ways of things happening. So when he did that is just based on the actions of this operator on a two-particle system. And what he found was if you're only going to get singlets and doublets, he described this as being comprised, as if they were comprised of two SU2 groups. Two SU2 groups is what he thought of. But nature's even wilder. What turned out to be true was, after doing more and more weird combinations, what they found was that these nucleons actually obey SU3 symmetry, and this was also aided by the experimental discoveries of various other particles like pions, mesons, and so on, which we'll, I think, have a review of in next lecture. Essentially, right now from a modern standpoint, we know that pions, mesons, and protons and neutrons are just comprised of quarks. But then, just based on classifying them on their observed properties, these are all just masses, and and each of this is a particle, and this corresponds to this is the negative electric charge. This is no charge, and there was another quantity that was introduced that's called strangeness, for the sake of because they did see that they were being arranged neatly in this hierarchy. Why must there be this geometry? And when they did the math, they found out this is a representation of SU3, and they found out that there were three irreps, or three irreducible generators, and these three generators correspond exactly to three quarks. But obviously we know today that there are 6 quarks, and that's a story that we'll leave for a different day. But this is essentially one of the biggest culminations of group theory, where this I think I might be mistaken when I say I think there were 8 generators, sorry, and they've actually found out 8 quarks. Apologies, yeah, because this is usually called the eightfold way. But you can see, just by purely thinking in this picture, okay, my quantum numbers must correspond to some generator, and that generator must be an irreducible representation of that group. And what is that group? So so again, this can all be summed up in a single axiom or a maxim, take whatever way. Conserved quantity, symmetry. Neither's theorem, back again. And with this, I would sort of like to hand over the baton to Rishi to talk about parity and density symmetries. Thank you.
Okay, so good evening, everyone. So previously, Pugazharasu talked to us about the mathematical part of symmetry and group theory. So what I will be trying to do right now is I try to bring the more intuitive or the more basic examples of symmetry and its violations in particle physics. So the first topic that I'd be focusing on is the parity transformation. So what is a parity transformation? So I'm pretty sure we must have all heard about the mirror reflection or the mirror transformation, which essentially, as we see in the first picture there, gives us a mirror image of a particle in concern here. So if let's take that mirror image right there, we don't essentially just place a mirror, but instead what we do is we perform a mirror operation on it. So what it essentially does is it gives us the mirrored image of the particle that we are taking into consideration. But the mirror transformation isn't exactly what we call the parity transformation. So as we see, the contrasting difference between these two pictures on the top and bottom is that the direction of motion is also switched in the parity transformation, while in the mirror transformation, the direction of motion is left untouched. So we'll try to focus on the consequences and what we call in particle physics as the parity violation in the next slide. Okay, so go on. Slide. Yes, so what we have in this image right here is a spinning cobalt nuclei. So as this cobalt-60 nuclei decays, it essentially emits beta rays or electrons preferably in the same direction as the spin of the cobalt nuclei. But what we see here is if we perform a parity transformation on that cobalt-60 nuclei, we'll essentially get the picture here only represents the mirror transformation, but what we usually take in consideration is a parity transformation. But what we notice here is that although intuitively we do get a parity transformation and we get the mirror image and invert the direction of motion, what happens here is that the picture there no more holds true in the physical realm, because the beta rays or the electrons is always gonna get ejected in the same direction as spin, but in the mirror image right there, it's in the opposite direction. So what do we have here? We have something called as the parity violation. Okay. So what does that parity violation tells us? That although there is a parity transformation, but it doesn't exist in nature as we see of it right now. So this parity violation might be, in small or insignificant for us, but this was one of the most eye-opening violations for physicists, because we thought the parity transformation was supposed to, hold true for all quantum mechanical or particle physics processes. But what we see here is that it's a very elementary violation of the parity transformation. So what we call in particle physics is that this violation of the parity transformation, or is called maximal. So in the next slide there, we'll be talking about helicity. So here we see a pion decay, a negative pion decay, right? So on the left we get a antineutrino, and on the right we get a muon. Okay. So then I think I forgot to add this image into the PPT, but then I put it in hall text. So we have a small representation of what helicity means. So when the direction of spin is the same as the direction of motion, it's called helicity of +1, or we call it right-handed. And if it's the opposite side, as in the spin is in the opposite direction of motion, it's called a left-handed particle. Okay. So just a second. Yes. So if we take this pion decay, right? So what do we get? We get uh, a muon and an antineutrino, right? So then we can establish, see the muon, we can establish the spin of the muon, right, from experimental results. And we know that the pion spin is 0 because it's a meson, right? It's a pi meson. Sorry for the disruptions. It's just my dog's just howling. So, so yes. So because of the fact that our pion right here has spin 0, we know that the ejection or the decay of these two particles right here, the muon and the antineutrino, are in opposite directions, right? So we know the direction of motion, and from the direction of motion, we can also determine the helicity, right? So this thing, I kind of skipped a small concept there. So this is experimentally determining the spin of a neutrino and an antineutrino. So before that, I'd like to take you back to a bit of uh, SR and some Lorentz invariance, right? So imagine if we take an electron which is right-handed, right? So like in this image right here, so it's moving. Just a second, just a second. Sorry. So where did I leave it? Ah, yes, an electron moving, a right-handed electron moving with the direction towards the right. Okay, with the same spin. Let's say it's spinning with the direction of motion. So imagine if we travel with a velocity v relative to the electron, we can know what happens is if we move at a velocity greater than the electron, let's say, from our perspective or our observation frame, we get to see that the electron is moving to the left, even though in an inertial frame or in a rest frame, we can see that the direction of motion is towards the right. So what have we done here? We have essentially reversed the helicity of the electron by us moving in a reference frame that is relative to the um, electron, Seringla. But then here's the thing. Let's take a neutrino or an antineutrino, which is massless, unlike the electron. We know that the neutrinos and antineutrinos travel at the speed of light, which is the barrier, right? Which is the speed barrier of the universe, or which simply states that no other observer can travel faster than the speed of light. So when that occurs, what essentially happens is we can never reverse, or we can never reverse the helicity of a neutrino or an antineutrino, right? So this itself is a violation of Lorentz invariance, right? Because we are unable to reverse the helicity of that antineutrino, right? So if we take a neutral pion decay, right? So it essentially decays into two photons, which are
Rishi,
equally
your voice
left-handed
is
and equally
breaking up.
right-handed. Yeah, Pugal?
Your voice is breaking
Ah,
up.
yes. Is it better now? Sorry, it's the
His voice is fine. Like,
yeah. It's my internet connection suddenly went off in the middle. I guess
no, that's fine only. Though.
it's fine now. So
Okay, carry on. Yeah.
yeah. So then, what essentially, just I'm just going to sum this up. What essentially our parity violation says is that all neutrinos are left-handed, right? And all antineutrinos are right-handed, or which in terms of helicity, we know that I explained previously, the same side spin, same direction of motion is called left-handed or right-handed, right? So that essentially sums up our parity. So if we go down a bit, hello. Yes, so we come up to charge conjugation. Okay, so what is charge conjugation? It's even more simple than our parity transformation. So charge conjugation essentially is an operation which you apply on a particle, which doesn't just reverse the charge of the particle, but then instead completely inverts inverts all of the intrinsic quantum numbers, but then leaves the properties such as mass, spin, and velocity and all of that unchanged. Right. So what does our charge conjugation do? It essentially changes our quantum numbers such as charge, strangeness, beauty, and all of those quantum numbers. Essentially, what it does is it gives us the antiparticle. Right? If we apply the charge conjugation to a particle, it gives us the antiparticle. Okay, so how far are you guys there? So yes, so we see that charge conjugation is also violated by the weak interactions because if we see the pion decay, right? When if we charge conjugate that, we only reverse the quantum numbers, but we do not reverse the helicity. And we know that all neutrinos are left-handed and all neutrinos are right-handed. Sorry, all antineutrinos are right-handed. But then in our pion decays, so in a positive pion decay, we get a neutrino, and a negative pion decay, we get an antineutrino. If we only apply the charge conjugation to these, right, we do not reverse the helicity, but then we only get the antiparticles. So we see that the decays do not hold true for if we only apply the charge conjugation transformation, because we will be completely disregarding the helicity of the particles. Okay, so we can see how the particles or the weak interaction violate charge conjugation. Next thing, so we'll now be looking at something called the CP transformation, or more or we see how the CP transformation is violated. So what is CP transformation? It's just a combination of either you first do the parity transformation and then you do the charge conjugation, or you do the charge conjugation first and then the parity transformation later. So now we can see that the weak interaction what's it called? The weak interaction equations or the decays are now satisfied if we apply a CP transformation to them. Right? So then we get an electron and then a positron, but then our spins are also the helicity of this is also satisfied. But then where does this CP violation? So it was long regarded that okay, fine. We thought the charge conjugation was violated and the parity transformation was violated. So now, if we add both of these and we try to do a transformation, we see that the weak interactions do not violate CP transformation. So the scientists were pretty happy with their discovery. You can say, okay, fine. Our CP transformations are left is a perfect symmetry and it's not violated by any particle processes. But then in came the kaon or the k meson decay, right? So then we saw that the kaon decays completely violated the CP transformation, the CP transformation, because of the fact that just a second. Yeah, because of the fact that usually a neutral kaon decays into K1 and K2. Okay, and I'm just putting this very abstractly because I didn't put in all the equations and all of that. So then I'm just going to put this abstract. So essentially, a neutral kaon decays into K1 and K2. Okay, and then K1 decays into further into two pions, and the K1 decays into two pions, and K2 decays into 3 pions. But then experimentally we saw that the K that the K2 pions, sorry, the K2 kaons also decay into 2 pions, which was bizarre because it's not allowed according to the CP transformations because of some calculations and the eigenstates of the CP transformation where didn't hold true for our kaons. So we found out that yeah, again, uh, our kaons completely violated the CP transformations, and yet we couldn't find a perfect symmetry in the world of particle physics. Okay, so then next came the TCP theorem. Okay, go down. Yes, so the time reversal in TCP theorem. Okay, so time reversal is pretty intuitive. It doesn't need much of explanation. So essentially, time reversal is you're just reversing a process. Let's say any decay, we are just reversing the time uh, time frame or the flow of time, which is bizarre if you think about it. But then intuitively or mathematically, it can be taken into consideration. So we can essentially reverse time, or time reversal essentially just reverses the decay processes, okay, which is also another what do you call a transformation in particle physics. And then we saw that time reversal here till date, none of our experiments have proven any violation of the time reversal transformation. Okay, and then here came the TCP theorem, which is a very important theorem in particle physics, which essentially says that it is impossible to construct a quantum system or a quantum field theory that completely violates our TCP theorem, or which TCP theorem is essentially the same as CP. Uh, what do you call the CP symmetry? But then now adding a time reversal component to it, right? So I guess that is all for now. It was a very short one because I don't know. I just didn't want to include much math and then just try to get it as intuitive as possible. So